Okay, let me switch windows. Okay, I want to remind everybody that you're getting your second exam a week from today. It'll be the same room as the last time. I'll send out, as we get closer, I'll send out the information. It'll be through today's material. Wednesday, we'll have review. And once we finish reviewing, I'll continue with new material that will not be on the exam. Okay, so where are we? So the last thing we did was we played around when we did Chebyshev. And we did Markov. Were there any questions anybody had about any of these examples?
Yeah, Professor, I had a question on, I think, Markov's theorem.
Yeah, what about it?
I didn't really get on how Markov's theorem, I don't know, the proofs got me. I really don't understand the proofs.
Well, Markov's theorem is a very weak theorem. It's really its whole purpose is to prove certain results. For example, we wanted to prove that if all x values equal mu, for example, well, no, then it's a concept of trivial case. Forget that. Basically, Markov's theorem says if we want to estimate probabilities like this, then we can apply Markov's theorem. But that's basically how it's used. So you compute the mean, compute the variance, or whatever, and then compute. Use Markov's theorem to compute it. There isn't much more than that. And if you look at any typical homework exercise here, let me pull one up. Okay, let's say number 2. A coin is tossed 1,600 times. Okay. And the expected number of heads, let x be the number of heads. So the expected, so we're being told the expected number of heads is 800 with standard deviation equal to, what's the place? 20. I mean, by the way, in case you need it, sigmas of x squared will be 400, right? Estimate the probability, determine the probability that the number of heads will be between 760 and 840. So I say 840. Maybe rewrite this. So the probability between 760 and 840. So let's make this look a little nicer. What's the mean? The mean is 800. Maybe I should do that in red so you'll see the contrast. What you do to one side of an inequality, we do to another. So this is equal to the probability. This is between minus 40 less than x minus 800 less than 40. Or there's the probability that the absolute value of x minus 800 is less than 40. So this is what the problem reduces to. Now, this looks pretty much like Markov's theorem, where this corresponds to A, right? If you look at the, I'm sorry, A, and this is sort of, and this, according to the theorem, this is greater than or equal to 1 minus sigma squared over A squared. In this case, sigma squared is, I lost, what's sigma squared? Sigma squared is 400. And A is equal to 40. So that's 1600. If I did that right, what's out? That's equal to 1/4, 3/4. So I just proved that the probability that X minus 800 less than 40 is at least 3/4. So again, if you look at the problem said, okay, where's the problem again? Estimate the probability there'll be between 760 and 840 heads. Now, it may in fact be that that there are a lot more. In fact, we're going to discover how to do this problem exactly later on in this chapter, I think section 2.12. But this gives us an estimate on this result. Part B is very similar. Whereas if you look at a problem like number 5, you're being told the probability that X is greater or equal to 0 is 1. That means X is non-negative. You're being told that E of X, I lost the place, is equal to 3. And you're asked to estimate P of X greater or equal to 4. Well, this is a straight application of Markov's theorem. I didn't put the Markov's theorem down here. Remember, Markov's theorem says the probability that X is greater than or equal to A is always equal to, or at least the expectation I think I used the letter C in the book, divided by A. So in this case, the probability that X is greater or equal to 4 is 3/4. Simple application of the two theorems. Naeem, is that, you got that? So they're just used to estimate various probabilities. They don't give you very good estimates at all. But they have theoretical consequences, and that's why they're important. Anybody else have any other questions? Okay. So today I want to talk about jointly distributed random variables. And we'll do everything in the context of an example. So let's suppose I have an urn. And in my urn, I have 2 red marbles, 3 white marbles, and 1 blue marble. And I'm going to draw 3 marbles without replacement. I'm going to let X be the number of red, and Y be the number of, which one do I do in the book? I'll do the same one. And Y is the number of white. And I want to make some observations. There's nothing new here. So let's look at each random variable separately, and then we'll put them together, and then when we put it together, we'll get all the notation that we need. Okay, so we have X and Y will be the number of red ones. And the notation is P of X and Y, or if you like, P of X equals I. It doesn't make a difference. In this case, X and Y and I are the same. So what can happen? We can get no red. We can get 1 red, or we get 2 red marbles. right? Because there are only 3. So if we look at the number of red marbles we get, we know, well, there are a total of 6 marbles here. So the probability of getting no red means I'm drawing 3 marbles from the 3 white and the 1 blue. And that, by the way, turned out to be equal to, I think it's 4/20. If I get 1 red, then I'm getting 2 from the other 4. Oops. Which turns out to be 12/20. Now if I want 2 red, but from the other 4, I'm getting 1 over 6/3 again. And that's equal to the complement, of course, which is what? 4/20. And we'll make some observations in a moment. Now I'm going to do the same thing for the Y's. And just to use a different notation, I'll call it Q of Y sub j, which is the probability that Y equals Y sub j. So I can get, for the whites, I can get, sorry, what color is this? Yeah, I can get no whites, 1 white, 2 whites, 3 whites. In each case, the denominator is 6/3. And I'll just fill in the numbers here. You know how to do this. 3 out of 3. And that gives me 1/20. Here I get 3 out of 1. Then 3 out of 2. Which is 9/20. Excuse me. Here I get 3 out of 2. Again, these are the exact numbers in the text. I'm purposely using those. That's 9 out of 20. And 3 of these is 3 out of 3. 6/3. And this turns out to be 1/20. Okay. So notice, by the way, sometimes I say x sub I, or sometimes I just say I, because it really means the same thing here. X sub I is the number of, what color was it? Number of red. So whether I call it x sub I or I doesn't make a difference. Similarly for the Y. Okay, and so but the kind of question we're now interested in is a little different. We might ask, what's the probability I get let me explain what this means. I could also write this as P of x sub I, Y sub j. And this is the probability that I get x sub I white, x sub I red and Y sub j right. So for example, what's the probability that I would get x equal 2? How many marbles am I choosing? 3. Y equals 1. Or for shorthand, I would write that as P of 2, 1. So we can answer that question as well, and then we'll make some observations, okay? So what I want to do is I want to redo what I just did in one table. So rather than look at the red separately and the white separately, let's play the following. X, Y, Okay, the values that X can take are 0, 1, and 2. Gonna put an extra row in it, folks. And the values that Y can take are, oops, that's not gonna be enough room. I'll just put the lines in afterwards. Y should take on the values 0, 1, 2, 3. Now I need more room. Okay, and I'll just fill in a couple of numbers. So let's ask us the following questions. What's the probability X equals 0 and Y equals 0? That's the number I want right here. Okay. Well, if X is 0 and Y is 0, I'm drawing 3 balls. Remember what else is in the urn? What's in the urn is just 1 blue. And that's impossible. If I'm drawing 3 balls, X and Y both can't be 0. So that probability would just be 0. What's the probability X is, so this was 0. What's the probability, let's say X is 0 and Y is 2. Well, if X is 0 and Y is 2, again, remember what's in the urn. If X is 0 and Y is 2, means I'm getting 3 white, right? I'm drawing 2 whites from the 3, right? X is 0 and Y is 2. I lost my place. X is 0, Y is 2. So from the 3, I'm drawing 2. And from the other remaining one, I'm drawing 1. Divided by the total number of things I get is 6, 3. Let me do another one for you. What's the probability that X is 1 and Y is 1? Say this one right here. Then I'll just fill in the chart. The probability that X is 1 means from the, where are they? From the 2 reds, I'm getting 1. So this entry from the 2 reds, I'm getting 1. What am I doing? 1, 1. I'm getting 1. So what's probably I'm getting 1 and 1. Something's not right. Oh, I'm only drawing 2 in total. I'm sorry. So from the other 3, I'm drawing 1 over 6, 3. So if I do the computations, let me just give them to you here. Let me make some observations. Are there any questions about any of these numbers? We'll do it again. So X you can take on the value 0, 1, and 2. Y can take on the values 0, 1, 2, 3. And if we actually do it, we'll see the numbers are 0, 0. I'm trying to read my handwriting here. That's 3 out of 20. 3 out of 20. 1 out of 20. I'm just copying what I have in the book now so we can talk about this. And then we have 0, 4 out of 20, 6 out of 20, 0. And then we get 1 out of 20, 1 out of 20, 0. One out of 20. I'm sorry, this is not 1 out of 20. So it's what? 3 out of 20? 0, 0. All right, I think I have them all now. And now I want to add an extra row and an extra column. Now this column, this sum is going to be P of X of I. I'm just going to add up the row. If I add up the row sum, what do I get? I get 4 out of 20. The next row sum will be 10 out of 20. Oh, I lost something. 6 and 4. 6. I'm sorry, this is a 6. This is a 12. And the last one is 4 out of 20. Similarly, let's add up the last column. Call it Q of Y sub J. This would be 1 out of 20, 9 out of 20, 9 out of 20, 1 out of 20. Now make the following observations. If you add up all the Q's, you get 1. If you add up all the P's, you get 1. So look at this one table. This one table combines all the information in the two separate distributions that we had before. So here's the probability distribution. So now I've given you P of X sub I, Y sub J. This table gives you the probability distribution for it's called a joint distribution. So for example, if I want to know what's the probability that X equal 2, well, I can get that right from this table as well. If X is 2, what's the probability that X equals 2? X could be 2 a whole bunch of ways, right? X could be 2 and Y could be 0, Y could be 1, and so on. It would be 4 out of 20. By the way, if we look before, when X is 2, did I work it out? Yeah, it's right here, 4 out of 20. So a whole bunch of things to observe. So let's look at this table. Again, getting the table is very simple. It's just a simple hypergeometric probability, and we have to work it out a number of times. But the important thing to see is we got a lot of information in this particular table. Firstly, notice if you sum up all the probabilities, it doesn't make a difference which way you do it. What must you get? 1. So the sum of all the interior numbers must always give us 1. So the row sum, notice the row sum is the last row, is the sum of all the probabilities that Y is equal to Y sub J. And the column sum is the sum of all the probabilities for the X variables. And the sum of all the interior numbers must give us 1, the sum of all the probabilities. So that's an interesting result in itself, that if you sum all the interior numbers, we get a 1. Similarly, if you sum just the P's, you get the total, you get P of X sub I. And similarly, if you sum just the over the columns, you get Q of Y sub J. What does that mean? That means when you go back to this table, if you want to find P of X equal 1, all I have to do is sum everything across the row, and I'll get what was it, 16 out of 20? I can't read my handwriting. 12 out of 20. I'm sorry, there's a 12. And I can ask questions like this. Oops, sorry. what's the probability that x equals 2 given y equals 1? Well, that's just a conditional probability, and that's just the probability that x equals 2, y equals 1. That's the intersection divided by the probability that's being given. Now we go back up here. The probability x equals 2 and y equals 1. That's 3 out of 20. And the probability that y equals 1 is the sum of this column. This is all the different ways y could be 1. And that's 9 out of 20. And that probability is just 3/9 or 1/3. That's pretty cool. Now, I didn't really need a table for this, for the probability distribution. It's nice to have this table give me a lot of information, and I'll talk some more about this. But I could have actually written this down in terms of formula, as I do in the text. You can say it's just a simple hypergeometric probability. But I want to make another observation. From this table, suppose I wanted to find E of x. Well, notice to do that, it's really very simple. E of x is a product of all the, E of x is equal to the summation of x of I times P of x of I. So in this case, what are the values that x can take? You take 0 with probability 4 out of 20, 1 with probability 12 out of 20, and 2 with probability 4 out of 20. So what did I say? 0 times 4 out of 20 plus 1 times 12 out of 20 plus 2 times 4 out of 20. What does that give me? 8 and 12 is 20. Something's wrong. 8, which turns out to be 1. If I did that right. Okay. Similarly, I can find E of y the same way. Well, I call it Q, I think. And what would that be? That would just be the product of the y's times the probability. It would be 0 times 1 out of 20. Plus 1 times 9 out of 20. Plus 2 times 9 out of 20. Plus 3 times 1 out of 20. And that gives you the answer. So we can talk about marginal probabilities and things of that nature. So again, so we now have the notion of a joint distribution. And there's a lot of interesting information we can get from this. So let's look at the example I do in the text. A coin is tossed 4 times. And I'll define the random variable x to be 0 if the first toss is a head. And I'll define it to be 1 if it's a tail. And I'm going to define the second random variable y to be the absolute value of the difference between the number of heads and tails. So let me look at the sample space first to make sure we understand what's happening here. So if I toss a coin 4 times, what could happen? I get head, you can get the sample space, of course, with a tree. I get 4 heads. I can get, let me just write these down. H, 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 T, H, H, T, H, 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 T, H, and H, H, T, T. And I want to do how I get it in the text. So if I get anything, 2, 3, 4. 1, 2, 3, 4. H, T, H, H. H, H, T, T. That's wrong. Okay. I get H, T, H, H, and H, T, H, T, H. H, T, H, T. Come on, one. H, T, T. H. H triple T. T, H, H. T, H, H. T, H, T, H. I just, please make sure I don't forget any of these. T, H. I lost my place. I have HTT, then I have T, then I have T triple H. Okay, etc. Because I'm losing my place here. Okay, they're all right here in the text on page 128. So let's suppose, so what could happen here in this problem is X is the first toss could be a head, and Y is the difference between the number of heads and the number of tails. So let's suppose I construct I get a head or a tail on my first shot. And I'll show you how I get all these numbers in a moment. And Y is the difference between the number of heads and the number of tails. Well, the difference between any number between 0. Well, what's the difference in number between number of heads and number of tails I can have? I claim it's 0, 2, and 4. And then let me illustrate how I get some of these numbers. If X is 0, means, what does that mean? It means the first toss is a head, right? In order for the first toss to be a head, what happens? I get H, 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 T, H, H, T, H. Because what I want to do is I want to compute this as an example. So I'm looking at HHHT, HHTH, HTHH, and HTTT. Notice every one of these cases, it starts with a head, and the difference between the number of heads and the number of tails, ignoring the sign, is 2. So these are the only 4 cases where X could be 0 and Y could be 2. And by the way, that's 4 out of a total of 16. Remember, if you toss a coin 4 times, there are going to be 16 possibilities. So the probability that X is 0 and Y is 2 would be 4 out of 16. In the same way, how would I compute X equals 0, Y equals 4? Well, that can only happen one way. If it starts with a head and the difference between the number of heads and the number of tails is 0, means they're all heads, and that's 1 out of 16. And the other numbers are gotten pretty much the same way. I'll let you do those yourself. And then I put in my last row. So just totally now, this is the sum of the rows. 7, this is a half. This turns out to be a half when you add them up. This is 6 out of 16, 8 out of 16, 2 out of 16. They're called the Q's. Okay, so I have this distribution, and I can answer any question I want about this. For example, E of X is easy to get. It's 0 times a half plus 1 times a half. E of X squared, if I wanted to find that, would be 0 squared times a half plus 1 squared times a half, and so on. Now, what I could, oops, I just dropped my pencil. Last time I did that, it stopped working. Fine now, folks. Okay. If I wanted to, I could define a CDF for a joint distribution like this. Remember, in the one-dimensional case, f of x was equal to the probability that x is less than or equal to little x. In the two-dimensional case, like this one, we could define, if we wanted to, f of x and y to be the probability that x is less than or equal to x and y is less than or equal to y. This isn't as useful as one would expect. But what is interesting is we can define independence in a multiple of ways. That is, x and y are independent if p of x of I comma y sub j, remember that's shorthand for p of x equal x of I, y equal y sub j, is equal to the individual product of probabilities. For all I and j. There are a couple of different formulations that one can give. I give out 4 different formulations in the text, but basically x and y will be independent random variables if the product of the probabilities is the same for all of them, which means it may be a little bit of work to prove that the joint distributions are independent. If you look at the text, I do an example for you where I just illustrate I give you the following table. If you have your book in front of you, it'll be easier. If you look at the table on page 130, I can bring that up. Hold on, let me do that. No, I can't bring it up on this computer. If you look at the table on page 130, maybe I should duplicate it here. One, two, 1, 2, 3. And let's suppose this is 0.06, 0.14, 0.15, 0.35, 0.09, 0.21. This is Q of Y sub J, P of X sub I. This is 0.2, 0.5, 0.3, 1, 0.7. Okay. Now I just replicated the table on page 130. So if I want to prove X and Y are independent, what I have to do is I have to first find P of 1, 1. And that's equal to 0.06. And then I observe that P of 1 is equal to 0.20, and Q of 1 is equal to 0.30, and their product are the same. I have to do that for each of the entries. So for every one of these entries, this is a 2 by 3. I have to show that P11 is equal to P1 times Q1. I have to show that P12 is equal to P1 times Q2, and so on. So if I can show that for every single one, then they're independent. And by the way, if you observe, if you look at the rows, notice that the rows are proportional to each other. For example, if you take the first row and divide it by 0.2, you get 0.03, 0.07, 0.03, 0.07, 0.1. Take the third row, divide by 0.03, you get the same thing. And that always happens when they're independent. Now, why is independence important? Well, first thing that I'm not going to prove is the following. If the random variable W is a function of some random variable X, and if the random variable, say V, is a function of some random variable Y, and suppose X and Y are independent, then so are W and V. That's a little messy to prove here. Okay, so I'm going to leave out the proof, but I will be using it in a little bit. I'll use this result very shortly. So again, if we have any two random variables, X and Y, any function of these random variables are independent. Now, that means, for example, if X and Y are independent, that would then imply that X squared and Y squared are independent. Or e to the X and e to the Y, whatever that might mean, are independent. Or X minus mu squared and Y minus its mean squared are also independent. All right. So let's suppose we have the random variables. Let's suppose W is a function of the random variable x and y, who have joint PDF probability mass function P of x, y. We define the expected value of W. Remember, W now is a function of two random variables, x and y. So I'm now extending the definition of expected value times P of x sub I, y sub j. So in the one-dimensional case, remember the expected value of a single random variable x was just a summation of x sub I, P of x sub I. Now we have a two-dimensional random variable W that depends upon x and y. And we've now defined its expectation. So let's talk about this a little bit. So I've defined E of W to be the double sum of W of x sub I, y sub j times P of x sub I, y sub j. So notice it's a simple generalization. But now let's make an observation. Special case. Suppose the random variable W is nothing more than the sum of x plus y. Then what happens? Well, this would become summation over I and j. It doesn't make a difference which order I take them, by the way. X sub I plus y sub j times P of x sub I, y sub j. So if we multiply this out, I have x sub I times P of x sub I, y sub j plus y sub j, P of x sub I, y sub j. Now, I can rewrite this as follows. Factoring out the x sub I part. And then the other part, I'm going to factor out the y sub j part. I'm allowed to interchange the order of summation here because they're finite. Now I know I'm summing all, in one case, I'm summing all the columns. This is just P of x sub I. The first case, I'm summing the rows, and now I'm summing the columns. Q of y sub j. And this is just E of x plus E of y. So I've just proven, using this extended definition of expectation, that E of x plus y is equal to E of x plus E of y. I promised to prove that to you a couple of sections ago. That's one neat result. Now, I want to look at the second case. Suppose W is X times 1. Then E of XY would be equal to the double sum X sub I Y sub J times P of X sub I Y sub J. Now, assume X and Y are independent. Okay, that's an assumption I'm making now. But if I make that assumption, let's see what happens. Then the probability becomes the product of X equal X sub I, Y equal Y sub J for all I and J. I can break this up now into two sums. Oops, second sum. Fix that. This is just E of X. This is just E of Y. So I've just proved two very important results. Okay, and these we need to use. So one is, in general, E of X plus Y equals E of X plus E of Y. And by the way, this generalizes to any number of random variables. I just did it in the case when there are two random variables. And the second result is if X and Y are independent, then E of XY equals E of X times E of Y. And I want to make a note. No, there's an example in the text where I do this. Note the converse is false. What do I mean? It's possible to rig up an X and Y that are not independent and E of XY equals, that is, this condition, if they're independent, this condition is true. However, it's possible for it not to be independent, for that condition to be true as well. So it's not the converse isn't always true. By the way, one useful example that we're going to use in a couple of days. If X and Y are independent, look at e to the tx, e to ty. Well, that's a function of these random variables. According to the theorem I proved above, it's equal to the product of individual expectations. So let's look at an example or two, just to show you how do you compute computing E of XY. Now, let me tell you why this is important. You might recall that when we looked at V of X plus Y, we found out that this was equal to V of X plus V of Y plus 2 times E of XY minus E of X times E of Y. And I might have mentioned that this is called the covariance, which we'll talk about soon enough. But in computing this, we need to know how to compute E of xy. So one way of computing E of xy, let me just show you what happens. I just showed you that this is equal to the double sum of x of I, y sub j, times p of x of I, y sub j, over all possible products, which means you can use a double sum. In fact, I'll show you in a moment you can do that, but I'll show you an easier way. So let's look at an example. Work went out here for with all right, fine. It does make a difference which one I use. Let me just pick up a table somewhere and here. So let's suppose we have the following distribution. One, two, 1, 2, 3. And let's suppose this is 0.12. This is 0.08, 0.30, 0.20, 0.18, 0.12. Okay. So we have this distribution right here. Okay, so now let's put in the extra row and column. Q of y sub j. What does this give me? 18 and 12 is a 30, so it's a 0.60. 12, 20, let's see, this is the 12. 12 and 8 is 20, is 40. This is a 20. This is a 50. And 30. Okay. So let's look at this problem. Firstly, if I wanted to compute E of x, that would just be 1 times 0.2 plus 2 times 0.5 plus 3 times 0.3. What would that give me? Whatever that gives me. If I wanted E of y, I would get 1 times 0.6 plus 2 times 0.4, and that would give me E of y. So now the question is, how do I compute E of xy? Well, I can show you the long way in a moment, but the short way is really very simple. Take all possible products and multiply them by the probabilities. For example, what are possible products? X could be 1, Y could be 1, and that probability is 0.12. Or X could be 1, Y could be 2, and that probability, I lost my place. X is 1 and Y is 0.08. Or X could be 2, Y could be 1. That probability is 0.3. Or X could be 2, Y could be 2, and that probability is 0.20. Or X could be 3, Y could be 1. That probability is 0.18. Or X could be 3, Y could be 2, and that probability is 0.12. And that would give us the answer for E of xy. Now, that's a simple way of doing it, especially if one of these is a 0. If one row is 0, you get a whole bunch of zeros going on. If you wanted to use the formula, I'll show you get exactly the same result. So then E of xy would be the summation of I, what are the values that x takes? Oh, come on. X takes on the values 1, 2, and 3. And y takes on the values 1 and 2. Multiplied by, this is a long way. So first let I be 1. So we get x1, yj, p of x1, yj. First I let x be 1, then I let x be 2, and then I let x be 3. Hold on, I'm sorry, this is a yj. P of x3, x1 is to x3 yj, p of x2 yj. So now what happens is I have 3 more sums. So x1, by the way, is what? X1 is 1. Come on, what's happening here? So let me just write this out a little more. X1 is 1 times yj, p of 1 yj, plus, remember each of these is a sum now, j equal 1 to 2, x is 2, yj, p of 2 yj, plus the third value of x is 3. Was that right? Was it 3? Yeah. Yj. What happened to my thing? Hold on, let's get that. So now I have to compute this sum, and there are going to be 2 more terms. 2 terms here and 2 terms here. So for example, suppose I did this one. Well, let me get rid of the sum. I would get 3y1 p of 3y1 plus 3y2 p of 3y2. And now, of course, y1 is 1, y2 is 2, p of 3y1, what is 3y1? Is 0.18. And the other one was, I'm sorry, y1 was 0.60, wasn't it? 3y1s, 3 y1 is, no, x is 3, y1 is 0.18. I was right, okay. And the other one was 3y2 is 0.12. And you do the same for this one and the same for this one. It's so much easier not to do it this way and instead look at all possible products. Let me just make sure you understood that. So, yeah, let me just make up a quick table. So, .1, .4. why don't I just do this instead? Okay, so let's suppose I made up this table. So again, I want to compute E of X of E of XY. So it's all possible product, but notice in the first row, it would be 0 times 1 times probability 0.2 plus 0 times 2 times 0.3. Notice everything would be 0 in the first row because of the 0 present. Second row would be 1 times 0.1 plus 1 times 2 times 0.4, and bingo, we got it done. So it's a lot simpler to do it that way. Okay, so where am I time-wise? All on good, okay. So let me just recap a little bit because there are a couple of important ideas here. So we define basically the two-dimensional probability mass function, P of X sub I, Y sub J. It has the property that when you sum up all its probabilities, you get 1. It has a proper, if you do something like this, you add up over a column, you get the probability that Y equal Y sub J. If you sum it over a row, you get the probability that X equal X sub I. Clearly, I never said it, but it should be obvious from all of this that all these numbers also have to be between 0 and 1. 1.0. Let's make a look at it. We defined the more general expectation. So we just generalize the definition of expectation to any number of random variables. Here, 2, but if I want to go to 3 random variables, that would work as well. It then follows that E of X plus Y for a joint distribution like this is equal to E of X plus E of Y. And this generalizes to any number of dimensions. And then if X and Y are independent, then it follows that E of XY equals E of X times E of Y. And we're going to see in that case, and then what I call the covariance, which I'm going to redefine in a section or two, which is E of X, Y minus E of X, E of Y will be 0. And I said the converse is false, meaning it's possible for the covariance to be 0 and then not to be X and Y not to be independent. Okay, so now that's section 2.9. So please, for Wednesday, do the homeworks in section 2.9. You're going to like them. They're very easy. And then we'll have a review. And then we'll have your exam on Monday. So let me just stop the recording.